So also this is for next week at chess. I'm going to talk about masks and masks against physical attacks, or M. So in the 90s, there were two very important papers for the world of embedded systems. There was the first paper on differential power analysis in 1999, and 3 years before that, there was the first paper on differential fault analysis. So both works started a whole research community on side channel attacks and fault attacks, and of course also countermeasures. So against side channel attacks, two important countermeasures are hiding and masking. And so you already know what masking is by this time. And against fault attacks, you need some kind of redundancy or repetition, like error detecting codes or tags. And then once you have this redundancy, you need to, there are three options on what to do with it. So you can use detection, correction, or infection against fault attacks. Now, suppose that you have an adversary which uses side channel attacks in combination with fault injections to launch a more devastating attack. Then we, of course, need to combine also countermeasures. So you could combine masking with some kind of redundancy. And then the big question is, how are we going to implement our cryptographic computation in a way that we go from the left side, the inputs masked with redundancy, to the outputs masked with redundancy? Suppose that we use Boolean masking, then this is very easy for linear operation. And the question is always, how do we do nonlinear operations, like multiplications? So masking is often seen as the embedded systems equivalent of MPC protocols, because they're all based on Shamir secret sharing. And recently, MPC protocols work with active adversaries. That means parties that actively deviate from the protocol and therefore introduce faults into computation. So we can see the combined countermeasures against side channel and fault attacks as the embedded system equivalent of active MPC protocols. And that gives us two ways to get to what we want. The first is to take an active MPC protocol and translate it to an embedded system implementation. And this was done last year with crypto, with CAPA, which is a provably secure scheme against combined attacks, but it's also very expensive because it's based on an MPC protocol. And then the other option is to take a masking scheme and extend it with fault detection or infection or something like that. So there are already some works that did this. At Crypto 2016, there was ParTI, which combines threshold implementations with error detecting codes. Also last year at chess, there was a polynomial masking scheme with fault detection. And this year, I'm presenting M&M to you, which is masks and max. So let's start with how you create an M&M implementation. Let's start with what can our adversary do? So what am I promising you for today? So security against an adversary that performs side channel attacks. For this model, we're going to use the deep probing model with glitches. The adversary can also inject faults. Now suppose that he injects glitches into the clock line or the voltage line, then those faults will be pretty random and they will be spread over the entire circuit, unlimited in the number of bits that could be affected. The adversary could also have a very precise laser which can change values exactly into a different value. Now those kind of lasers are expensive, so we're going to limit those kind of faults to certain parts of the chip by saying that at most D of the D+1 shares can be affected in that way. And then finally, we're going to allow the adversary to do also combined attacks. Now, M&M will provide security as far as we know against combined attacks that are currently in the literature, but we don't have the provable security like with CAPA, so we cannot know for sure about unpublished attacks. So the redundancy that is used in M&M is information-theoretic MAC tags. So it's not cryptographic MAC, but information-theoretic MAC tags. It's simply for every piece of data X, we have a tag, which is simply a multiplication in a Galois field with a MAC key alpha. So this MAC key alpha is secret, and it's for every encryption you're supposed to use a new one. And the goal is that, so for an adversary to be successful and change the calculation, you would have to change both X and the tag. And since alpha is secret, the probability that he's successful is 2 to the minus an, which follows from the size of the tags and from alpha. So then the question is, with these data blocks X and their tags, how do we perform a multiplication? M&M starts from a masking scheme. So let's assume we already know how to do a multiplication on shared values. The literature has a lot of possibilities for this: threshold implementations, domain-oriented masking, etc., etc. So we apply that mask multiplications to our shares of X and Y to get a masking of X times Y. If you do the same with the tags, then you get a sharing of alpha squared times X times Y, which is not a valid tag for X times Y. But we can easily correct that if we do an extra mask multiplication with a sharing of alpha inverse. And now we have alpha times X times Y, which is a valid tag for Z. But it's not very efficient, because if you see, one shared multiplication becomes 3 shared multiplications in M&M. So that's a scaling factor of 3, which is not great. But with this multiplication and linear operations, you can basically build a circuit for any algorithm. But we can do a bit better. Suppose you have a power map, like x to the power 3, and you already have your masked implementation for this power map. You can apply it to x to obtain x to the power 3, and you can apply it to the tags to get alpha to the power 3 times x to the power 3, which again is not the valid tag. But this is easily corrected with a multiplication with alpha to the minus 2. Alpha to the minus 2 is very easy to obtain from alpha inverse, because squaring is a linear operation. And the same goes for any other odd power map, as you can see, which is very useful because power maps are a popular tool in symmetric key cryptography for S-boxes. For example, also AES. The S-box of AES is based on a power map, the Galois field inversion, which is also the same as x to the power 254, which is sadly not odd, but no worries, because suppose that we can do an inversion masked, and we apply it to x and the tag, then we get x inverse, and we get alpha inverse times x inverse. And all we have to do to create a valid tag for x inverse is multiply with alpha squared, which again is very easy to obtain from alpha. So this is already very nice, because now we have a scaling factor of approximately 2 for the entire S-box of AES. So with these building blocks, you can create an M&M implementation for any cryptographic algorithm. And remember, you can use any existing masking scheme in the literature, so and plug them in here. So as there are many available, there are many different ways to create M&M implementations. Now we have our redundancy. So we have our data path masked, and we have also a data path for the tags, which is also masked. The question is, what do we do now to actually detect faults, or what are we going to do to provide protection against fault attacks? We could try to do a check that verifies that the tag is equal to what it's supposed to be, alpha times c. Now the problem is that implementing a check like this is dangerous, and it's easily vulnerable to combined attacks. So we're not going to do that. What we're going to do is use infective computation. So this is a proposal from 2012, where you have repetition against fault attacks, and then so you get 2 ciphertexts at the output. And effective computation is used so that if these ciphertexts are not equal, then you want to output a random ciphertext, and that way an adversary cannot get any information from that faulty ciphertext. So how they do it is just by adding the difference between the 2 ciphertexts multiplied with something random to the ciphertext. Sadly, this proposal was broken 2 years later, and also many other effective computations have been broken, because there was actually a problem with R, there was a bias on R. So we're going to do something similar minus the flaw. So we have our tags and our data path, and we're going to make sure that we output something completely random if they're not consistent. So every share of the ciphertext, pointer that way, is is XORed with something with the difference of what the tag is in reality and what the tag is supposed to be. So alpha times C. If we look at the unshared ciphertext, that means that if the tags are consistent, then this part is 0, so we just output C. If there is something wrong, then this part will be non-zero, and then it is randomized by R, so we output a random ciphertext. But remember, this is all happening in shared form. So we checked that the bias is that there is no bias in this case. So suppose that that something went wrong, and you actually have a faulty ciphertext at the output, so with a fault delta. Then what we get after the effective computation is this, and then we want to check that this mask is actually uniformly random. So delta times 1 plus R alpha has to be uniformly random, and we can easily check this. And it is the case because alpha is uniform in the field, and R is uniform except for 0. R cannot be 0. So you can easily check this with a Python script that it works. So we applied M&M to AES as a case study, but remember, we only tried one of many options because there are so many different papers on how to do masked multiplications or masked AESs. We chose to use the S-box from the Knudde from CHESS 2016, but depending on your priorities, you might want different trade-offs in area or latency, and you can choose any other S-box in literature. And then it's very difficult to compare to existing schemes because everyone uses a different adversary model or a different cipher or a different library. So we decided to look at the overhead factor of the combined countermeasure over only a side channel countermeasure. So when we compare to CAPA, we can see immediately that M&M is a lot more efficient. But that's also logical because CAPA has a very strong adversary model and has provable security. So this is really logical. Then we also compare to ParTI, but they only provided first order implementations. We can see that also the overhead factor compared very nicely. Keep in mind also that ParTI has a different adversary model. In their case, faults that are limited in Hamming weight get detected with 100% probability, and faults that have a higher Hamming weight than a certain limit, they don't get detected at all. So then we also did some evaluations of our implementation. For side channels, we took 50 million traces, and we did a bivariate t-test. So here we are combining traces of length 1,000. We're combining every sample with all the other samples. Without the PRNG, so without the countermeasure, you can see that leakage is detected in a lot of places with very high t-test values. And then when we turn on the countermeasure, all the leaks disappear, and we stay nicely under the threshold of 4.5. We also did a fault evaluation. Now, in the state of the art, there's not really a common method to verify faults yet. So we took our hardware description and we adapted it with some extra XOR gates here and there, which also gave some extra inputs to the circuit, with which we could decide where to inject faults. And these inputs we directed it randomly. So we did 50,000 experiments where we injected randomly some faults. And out of these 50,000 iterations, there were 189 times where we got a faulty ciphertext at the output that was not infected, which is about, so that means that about 99.6% of the time our countermeasure was working. And this corresponds to the theoretical rate of detection of 99.6%, so that's nice. This was only a very experimental thing. It's not comprehensive because there's nothing in the literature that we could use. But in the meantime, it has been extended and optimized more. And for this, I'm going to refer the people at CHESS to the poster session where Victor will be. So to conclude, M&M is a lot cheaper than CAPA. But it has a stronger adversary model than ParTI because it's not limited in Hamming, faults are not limited in Hamming weight. It's very versatile because you can use any of the existing masking schemes, any of the existing AES implementations, also future masking schemes and AES implementations. In the paper, we also describe how you can combine the infection with detection, because for some applications you might want a flag that says like, hey, something went wrong, except of just a randomized ciphertext. And then there are some things that we can do for future work. So first of all, we need provable security against combined attacks. Second of all, we don't have any verification tools to check combined countermeasures against combined attacks. And finally, we could optimize M&M instead of always correcting the tags. We could also just keep track of the changes in alpha instead of always correcting it. Thank you.